Okay, hey guys, these are the videos for tutorial 7, and I know that so I'll just say right now, this is the first homework assignment after the midterm. The midterm grades, the midterm was not quite what I was expecting. I was not expecting him to do a rotated frame. As I was telling a few other students in office hours today, every time I think that he's not going to do something, he manages to surprise me, and this was no exception. So the tricky part of this year's exam was the rotated frame. And I hopefully he'll go over a little bit of that on Friday. The solutions should be posted eventually, maybe later this week if they're not up already. So I'll let you go through them. And then if you have any questions about that, we can schedule a meeting for her to go over it. This current homework assignment, everything about this is just solving indeterminate frames and beams. So you have an indeterminate beam here, another indeterminate beam, and an indeterminate frame here. Now, although we're using the word indeterminate, don't get thrown off by that. You've been analyzing indeterminate structures for quite a while now. So if we go back to like tutorial 6, for example, this is the last homework assignment. It's been a couple weeks because you had the exam. But in this homework assignment, you had to find the force P at A in order to get zero deflection at A. All that means is that this is actually equal to some pin-pin structure instead of a pin-roller structure. So if I had, for example, this was A and B, then I have 4 reactions, right? I had AX, AY, BX, BY. But now AY is equal to P. So I actually solved for force P first, and then I ended up with an indeterminate structure. So what we were really doing in the past was indeterminate structures in reverse. And now we've kind of just thrown on this indeterminate name onto it, but don't get thrown off or discouraged by that. You're going to do the same thing. The only thing that changes is how you start your process. Everything else after that, once you've figured out how to start it, everything else just follows through. So what do I mean by how to start it? You have 4 reactions here, right? You really, for indeterminate structure, we want to convert this to a determinate structure by adding an equation of condition. So for this problem, for example, I have this cantilever, right? I have this cantilever. Why am I using a pen? I should be using markers. Where'd my markers go? But I have these four I have 4 possible reactions. I have 3 at A. So for example, if I have my cantilever here, and it goes over a little bit, I have a Y, AX, I have the moment at A, and I have this point load out here, which is called BY. I have 4 reactions here. Now, there is no singular correct method to do this. I can release any one of these, except maybe this horizontal one, and I would be able to solve through this without any issues. So what do I mean by that? I mean that I could, for example, try to turn this one into a pin. Right, this would be one solution, and I would have some force N applied here, and I would want to find the reactions, the force N required to make the rotation here 0. So N required for theta A equals 0. I'm sorry, I know my handwriting is horrible right now, but well, not right now, in general, but well, hopefully this is still legible here. So this is one thing I could do. I could remove the force at B. I could put a force at B, so I can remove the roller at B. In other words, I'd be left with a cantilever, and I can just find the force BY. Find BY for delta B equals 0, and this is something very similar to what we've done previously. Another one I could do is I could convert A into a slider, right? So One of the things I could do, this one I think would probably be the most tricky, but you could imagine a scenario where, for example, this was a slider like this, and you forced, you just had some force here, AY, and you're going to find AY for delta AY equals 0. So I can do any one of these three. Now, of course, the trick with your examination and your homework and in general when you're doing this is trying to find the one that has the least amount of work. And it's really up to you. Personally, I find cantilevers to be the easiest thing to work with. So in this case, I would get rid of B, for example, for this particular problem. But any one of these would work. You might have a little bit more work to do in some of them, but really once you have your moment diagrams, you're pretty much set. The reason why I like cantilevers is because it's very easy to use, for example, moment area instead of virtual work. In some cases, like moment area is really it's a very specialized tool, but when you can use it, it's very powerful. In this case, I can use moment area because I know if I removed by, I would be able to use moment area here because I know that the tangent here is 0. And I can use that to find my deflection in one step. I just need to know the moment diagram and the location of the centroid. Using virtual work is perfectly fine for any of these other cases. And even for the cantilever case, using virtual work is absolutely fine. If you're using virtual work, always remember to go back to this table. So this table, let me just lift this up, I guess. This table here is available online. There are a couple corrections I need to point out here. So this one, I believe it was in here, I want to say. In this version, it's corrected, but in your version, I believe there's a 1 in front of this, or a 2 in front of this. You need to cross that out and turn that into a 1. And then Hong, the other TA, pointed out that there is an error in this last one here. This should actually be b squared, not a squared. But using this table is definitely the easiest way to solve many of these problems because it greatly simplifies your work. So with that, that's really, it's kind of hard to go into details with some of these problems just because most of it is in the setup, and if I show you the setup, it's gonna force you, it's gonna drive you all into a single solution, and I kind of want to avoid doing that. So I will just say that you can use any one of these three methods. I think this particular one, this last one here, would be the most tricky. These two would probably take about the same amount of time to analyze. And yeah, this first one, I don't really have any specific comments on anything else in here. So, like again, if we just do virtual work in general, we can use this as a general example for virtual work. Let's say, for the sake of argument, I'm going to go ahead and, or for the sake of demonstration, I'm going to go ahead and remove the reaction at B. I would end up with something that looks like this. This is my, I'm sorry, this is like this. Some force here. Instead of working with this, I'm going to split this up into two systems. I'm going to have a P1 system with my distributed load by itself. I'm including this overhang. You can ignore this overhang for the most part and just add it at the very end. It's not going to, there's no load on here. It's a free cantilever, so there's not going to be any moment or deflect, or there's not going to be any moment inside this section for any part of this. So this is my P1 system, my MP1, and I also have an MP2 system, and that is due to B1. my Q system is going to be very similar. Okay, it's just going to be my Q system here is just going to be this one times, or it's going to be this one divided by by. And so this is my MQBY system. Now with that, I would just go ahead, I would draw the moment diagram from each of these. So whenever you're doing this diagram, I would just go ahead and draw the shear diagram first. So let's do the MP1 case, for example. In the MP1 case, my shear diagram would look like a triangle. Right, it would go up first, and then it would just go down to 0. This is my shear diagram. My moment diagram would start off, so this is all positive. If I draw my moment diagram positive downwards, I need to start off with some negative value. I'm going to have a large positive slope, and it's going to become less and less positive. So my moment diagram would look something like that. It would just be a concave down, concave. Well, this is my positive upwards. So this is technically a concave down parabola, drawn concave upwards. And yeah, so this would be my MP1 diagram. I would take the moment diagram from my MQ system, multiply it by the moment diagram of my MP1 system, take the moment diagram of my MQ system, multiply it by MP. So in other words, I have that, and that would be my deflection. So my delta B is equal to MP1 times MQ on EI plus MP2 on Q, MP2 times MQ on EI. I should be formal when I put the integrals in here. And this should be equal to 0. And I would just solve for By. Once I have By, I can draw my moment diagram normally. Right? Once you have By, find out what your reactions should be here. And from there, just draw your shear diagram and draw your moment diagram. So there isn't too much else for this problem. I'll leave it at that for now. And if you have any other questions on problem 1, feel free to send us an email.